Welcome back. We just learned about collision theory, and we talked about how all those different things, orientation factor, collision frequency, and collision energy, affect the ability of reactions to happen and the speed at which they happen. And then we drew those diagrams that showed activation energy was really the important thing in determining the speed of reactions. If you have a high activation barrier, your reactions are going to go slow because there's very few molecules that have enough energy to overcome that barrier. If you have a very low barrier, your reaction is going to be very fast because you have a lot of molecules with enough energy to overcome that barrier. It turns out that a gentleman by the name of Arrhenius was able to come up with a relationship mathematically that related those two things directly. And what he said is that K, your rate constant, right? There's all sorts of K's in chemistry. K, your rate constant, is equal to Z times P times the exponent minus EA over RT. Right? And this is what's called the Arrhenius equation. It's usually written a little more shorthand as combining Z and P into something called A, and then taking the exponent of E to the minus EA over RT. So that whole thing is exponent. The EA and the RT are all part of that exponent. The Z and the P, what they actually stand for is Z is the collision frequency. This is an orientation factor. And then we know that EA is our activation energy. And so you can see that there is a relationship between collision frequency and orientation factor in the rate constant, but they're linear. But if you look at the relationship between K and activation energy or temperature in the rate constant, it is exponential. So there's an exponential change in rate with temperature. There's an exponential change in rate with activation energy. And it's actually a comparison of those two that we're doing, right? We're taking EA and dividing by RT. So we're saying we're comparing activation energy and temperature, but there's an exponential thing. If you raise your EA a lot without changing your temperature, you're going to have an exponential decrease in your rate constant and thus your rate. If you increase your temperature, you're going to have an exponential increase in your rate constant. So really cool things. And but it turns out these collision frequencies, right, that's just a number. How often do these things combine, hitting each other per second? Orientation factor, just so you know, is usually a number between 0 and 1. 0 says that there's no orientation that these things ever react, and K would be 0. 1 says that no matter how these things hit each other, they love to react. And that would be if you have two atoms coming to each other. Spherical, but spherical is going to have an orientation factor of 1. But most other things have orientation factors of less than 1 because there's special orientations that are more likely to react than others. But it turns out those numbers are so unimportant that most people just combine them into this capital A that most people just ignore because we don't really care too much about it. Because the most important thing is that exponential term. You want to increase K, decrease K, you're going to use that exponential term to do it, not the linear terms. So this is the Arrhenius equation, and it's one that we're going to use a lot to try to relate activation energy to K. It's essentially just a plug and chug. As long as you know how to use exponents on your calculator, you should be able to do this one. The thing to keep track of is units, especially up here. You've got to keep track of your units because you cannot take the exponent of something with units. So you've got to make sure that your units cancel. What does that mean? EA, right, that's an energy. It's usually given in some sort of unit of energy, often in joules. R, right, we have two of them that we know. We've got 0.08205 liters atmospheres per Kelvin mole. We get 8.314 joules per Kelvin mole. If we're going to be canceling things, gosh darn it, I'm guessing we're going to want the 8.314 joules per Kelvin mole to be able to cancel joules, which means that EA, if we're given it in a different unit, we probably want to convert it to joules. Now, on the internet, you can look up R in just about any unit you want. I encourage you to just have one R and convert things to conform to your R rather than the other way around. Convert your R to conform to other things. Temperature is always going to be in Kelvin, otherwise it won't cancel your Kelvin here. So you got to keep track of those units, make sure you're doing those units properly. Here's a chance to do it on this next slide. You're going to use the Arrhenius equation to find the rate constant for a system with an A value of 7.65 times 10 to the 10th molar per second. So you can see those things are very large. Why? Because things hit each other a lot. Okay, so 10 to the 10th molar per second and an activation energy of 166 kilojoules per mole at 600 Kelvin. All right, so go ahead and try that one. What'd you come up with? Well, let's go through it. We're just going to plug things in. We got K equals 7.65 times 10 to the 10th molar per second times the exponent of minus. That minus is important, right? Activation energies are always defined as positive, just so we know. They're always positive because they're always comparing that reactant energy to the transition state. It's always a positive value. And so we're going to put in that 166 kilojoules per mole. Oh, kilojoules, that wasn't our unit of R. Let's convert that to joules by multiplying by 1,000. 160,000 joules divided by 8.314 joules per Kelvin mole times my temperature. I was nice, I gave it to you in Kelvin. If it wasn't in Kelvin, you would have had to convert it to Kelvin. Check our units cancel, Kelvins cancel, Kelvins cancel. Moles. Activation energy is in joules per mole, so that cancels there. And we have no units left in our exponent. That's just a plug and chug, making sure to put those parentheses in there, making sure you're dividing by 8.314 and you're dividing by 600, and you should get the answer of B, which is 2.7 times 10 to the minus 4th molar per second. If you got one of those other answers, it means you either put a positive in your exponent, or you forgot to convert from kilojoules to joules, or you converted your Kelvin by using 273. But you can see the huge differences by doing small mistakes. Those other ones are all small mistakes, but he went from 10 to the minus 4th to 10 to the positive 10th or 10 to the positive 9th. So if you didn't get that originally, try to plug it in your calculator again, just being careful about how you plug things in. So how else can we use the Arrhenius equation? Well, it's Chem 51, folks. So in Chem 51, if we can turn it into a line, we're gonna. So you've seen the integrated rate laws already. We turned all of those different concentration things into lines, and we're going to do the same thing for the Arrhenius equation. So if you start with the Arrhenius equation, K equals A e to the minus EA over RT, what we're going to do is we're going to go ahead and take the natural log of both sides of that equation. And so let me go ahead and just take a natural log there, ln, and as long as things aren't equal to 0, we're good. So we get natural log of K equals natural log. What are we going to do? Natural log of A times B is the natural log of A plus the natural log of B. So we're going to say natural log of A plus the natural log of e to the minus EA over RT. Well, natural log and e, they are opposite functions. And so this becomes the natural log, if my handwriting supports it, natural log of A plus a minus EA over RT. Oh, that's interesting. I'm going to do this, rearrange this ever so slightly and just say the natural log of K equals minus EA over R times 1 over T plus the natural log of A. I was just rearranging the previous equation. Why did I rearrange it like this? You guessed it. Y is equal to mx plus b. Y in this case is natural log of K. M minus EA over R. X 1 over T. And B is the natural log of A. So when we plot, we are going to plot our Y, which is the natural log of K, versus our X, which is 1 over T. And that's what we call an Arrhenius plot. The natural log of K versus 1 over T. And again, these are things we do in Excel. We have it do all that calculation for us, or Google Sheets, or whatever you want to use. What does it look like? It looks something like this. This is ln of K versus 1 over T for the decomposition of N2O5. And you can see it's this lovely, nice little straight line. What do we have for units? Ln of K has no units. 1 over T has 1 over K. So our slope is going to have units of 1, right? Nothing, over 1 over T, or just 1 over K, sorry, K for Kelvin, or just units of Kelvin. So whatever the slope is going to have units of Kelvin. I thought I had a slope for this guy, but I don't. We're going to go ahead and do an example in a little while. But what you do is if you had this slope, just that slope would be equal to minus EA over R. So the slope is minus EA over R. And again, that R should probably be your 8.314 in joules per Kelvin mole. But it's a neat way. So if you want to find EA, you just manipulate this equation and you get minus slope times R. Right, so it's really easy. To get the activation energy from an Arrhenius plot, you take the slope, you take the negative of it, and you multiply by R. You should always get a positive activation energy, which we do in this case. Since we have a negative slope, we take the negative of that, we're going to get a positive activation energy. If you don't get a positive activation energy, you probably did something. All right, so here's your chance. What's the activation energy of the reaction whose data is shown in this plot? So we've got some data there, natural log of K versus 1 over T. I've got a fit for it there that I did, and you're going to try to tell me what the activation energy is. You ready? Okay. What did you come up with? You're like, stop saying that. Okay. That's just what I say. We just said on the other thing that the slope is minus EA over R, or EA is minus slope times R, which is going to be minus 10,498. What did we say the units were? 1 over Kelvin, or Kelvin times 8.314 joules per Kelvin mole. If you do all that work, you find that you get a slope, or I'm sorry, an EA of 87,280 joules per mole. You can convert that to kilojoules by saying 87.3 kilojoules per mole, or answer B. So very simple to take data of rate constants and temperature. You take some natural logs, you take some 1 over temperatures. Temperatures have to be in Kelvin. Plot it, and your slope, if it's nice and linear, which it should be, comes out and you can get the activation energy. The reason this is so cool, folks, and it doesn't sound cool. You're like, oh, another thing to do, another thing to plug into there, numbers I don't really. But look at this, folks. The activation energy tells us the energy from the reactants up to this transition state. We don't see the transition state. We don't see what the molecules are doing, how they're reacting, how they're falling apart. We just see, did something happen? Did something not happen? Oh, look, we made this new product. But just by knowing some rate constants, we're able to actually figure out the energy of this transition state, the energy of this molecule when it's right in the middle of reacting. And to me, that's really, really neat. That just by taking a few data points at different temperatures, we can figure out something that's happening on a molecular scale, things we can't even see, and know their energies fairly precisely. I think that's cool. You might not think it's cool, but I think it's cool. So plotting's great. Sometimes you only have 2 data points. So some people will use the subtraction form of the Arrhenius equation, where they take Arrhenius equation for K1 and temperature 1. They subtract the Arrhenius equation for K2 and temperature 2. I'm going to spare you the details of the algebra and just give you the result. ln of K2 over K1 is EA over R times 1 over T1 minus 1 over T2. You could also just plot those 2 points and take the slope, and you'd get the same thing that you get here. You also, if you're going to go onto the internet, you might find that there's a bunch of different forms of this equation. One has K1 over K2, one has 1 over T2 minus 1 over T1, because all of those things are just negatives of each other. So you just have to pay careful attention to the negatives and the order of things. The way I have it, K2 has to be over K1, T1 minus T2, and you get a positive EA over R. If you switch anything, you get a negative somewhere, and that's okay, but you just have to pay careful attention to it. So that's what you'd use if you had 2 points of data instead of having a bunch of points of data. Not required, but on a test or quiz, that might be something that I make you do because you've only got 2 points of data and you just don't have time to do plots on a quiz. Let's go ahead and do an example of that one. We're going to take methane plus sulfur and make carbon disulfide and CS2 helps. CS2, and we're going to make some hydrogen sulfide. Look something like that. And we're going to go ahead and find some rate constant versus temperature data. So we've got K, 1.1 molar per second, and 6.4 molars per second in my temperature in degrees Celsius. is 550 and 625. And of course, I actually need my temperature in Kelvin. And so that's going to be 823 and 898. So we have this table of data. It's got 2 Ks. It's got 2 temperatures. We're going to use this to find our activation energy. So this is just a plug and chug kind of example, but I just wanted to show you what it looks like when we do this. So we've got the natural log. Let's make this number 1. Let's make this number 2. The natural log of 6.4 over 1.1. Our units are going to cancel, so if you want to leave the units out on that one, you're certainly welcome to. Is EA over R. I like to leave R as R when I do these and kind of do it towards the end. Just makes my life a little easier. But you are certainly welcome to plug that in earlier if you want. 1 over T1. Again, pay attention to the order. 823 Kelvin minus 1 over 898 Kelvin. There is some algebra to do there. I assume that you can do that algebra. Plug the 1 over 823 minus 1 over 898 into a calculator. Plug the natural log 6.4 over 1.1, right? Divide those two out. 1 over 823 minus 1 over 898 Kelvin. And then multiply both sides by R. If you do all that and you use your 8.314 for R, you should get EA is 1.4 times 10 to the 5th joules per mole, or 140 kilojoules per mole. And you'll notice I've been doing my activation energies a lot in kilojoules, even though when you do the calculation, it all ends up in joules. And that's just common. Activation energies are usually large enough that they're reported in kilojoules as opposed to joules. It's not absolutely required, but it is the convention that you will see activation energies reported in kilojoules. So I encourage you to do it just so you are sticking with convention. Okay, so now we know how to use the 2-point Arrhenius equation in order to calculate activation energy. Or you could use it to calculate a temperature. You could use it to calculate a K if you had all the other data. So that was our talk about the Arrhenius equation, a great way of relating rate constant to activation energy and temperature mathematically. Thanks.